Alright, suppose we have a piston full of an ideal monatomic gas in here, alright, and it is absorbing heat, or thermal energy, by heating from its surroundings out here, and then it's pushing on the piston to make it expand from an initial volume to a final volume. Alright, so what we're going to do is find the change in entropy for this process. And one key thing that we're going to look at is if throughout this process the gas stays at the same temperature. Alright, and this seems like a very contrived example, and it is. And we'll see why. But it's applicable to a more useful example. The case of a free expansion of a gas. So we'll look at that as well. All right. So first of all, because the gas inside this cylinder is not changing its temperature, the internal energy of monatomic ideal gas, right, is 3/2 N kBT. All right. All right, and the number of particles of this gas is not changing, and the Boltzmann's constant is constant, right? So the internal energy of the ideal gas only depends on the temperature. All right. For this problem, we're looking at the case where the temperature of this ideal gas is constant. So therefore the internal energy is constant. All right. We can see that any change in the internal energy has to be the sum of work and heat. So this is work done on the system, or heat or energy transferred into the system by heating. All right. So in this case, because the temperature is not changing, the internal energy is not changing, this change in the internal energy is going to be equal to 0. So in order to calculate the entropy change of this situation, what we need to do, right, the entropy change is equal to this change in energy by heating over the temperature at which it takes place. All right. So we need to find this dq. So we need to find this. That's going to be very difficult to do if we did not have this relationship right here, because we know this expansion takes place, and we know the volumes at the beginning and at the end. We can solve for the work part. All right, and then the work part is going to be equal to the amount of heat. So what's going on is this system is absorbing heat from its surroundings, say an infinitesimal amount at a time, and then it's doing the same infinitesimal amount of work on this piston. So this is a quasi-static process. So it's anyway, it's one you don't see in real life. And so we'll look at the change in entropy of the gas and of the universes as well. So the gas plus the surroundings. All right, so let's look at this dW thing. All right, that's equal to minus the pressure. Oh, why did I write W? This is a volume. Okay, pressure times the change in volume. All right, so to solve for the amount of work, that the gas is doing. We need to look at this here. So we can use the equation of state for an ideal gas. So PV equals nKT. This is Boltzmann's constant again. All right. So what we're just going to do is plug. We'll solve for P. So we just divide both sides by V. All right, and then plug that in here. So we have a minus n kV T divided by V multiplied by dV. All right, so this is our amount of our infinitesimal amount of work. All right, let's move to a new page. How about? So what we're going to do is look at this change in entropy. Okay, so now we're solving. If we bring one of these over to the other side, we pick up a minus sign. So this is equal to minus the infinitesimal amount of work over the temperature. All right, and we just solve for this dW. So the minus sign will leave us. This is a dV over T. Oh, and there's also a V on the bottom. All right, so our T's are going to divide out, which I guess makes sense since we're at a constant temperature. Well, I don't know, maybe it doesn't make sense. Okay. So the change in entropy of the gas, if we integrate this, okay, we'll integrate this other side as well, from VI to VF, N kV T, oops, no T anymore, NKB, and then dV over V. All right, N and KB are constants, they come out front. And then when we do the integral of the 1 over V dV, we just get a natural log. Like this. All right, so this is the change in entropy of the gas. All right, so now if we want to look at the change in entropy of the environment, we have to know how much heat was transferred from the outside to the inside. So it's the same amount as was transferred in. So we can just look at how much energy the gas absorbed by heating, and then that will tell us how much energy left the reservoir by heating. So maybe I took a little shortcut here and I went straight to integrating for the entropy, when what I could have done is just integrated for the change in the work, or in other words, integrate for the total work, I guess. In other words, the total energy transferred by heating as well. So let's go back and do that real quick. So the work, right, we're integrating the work is equal to the integral of minus P dV, or in other words, minus N kV T over V dV, from an initial volume to a final volume. All right, so this gives us minus N kVT, and then the natural log of Vf divided by Vi. All right, so here's our work, and then to get Q, all right, the total amount of energy transferred by heating is just equal to the opposite of the work. All right, so that's just equal to n kVt natural log of Vf over Vi. All right, so now to get the change in entropy of the reservoir. Okay, this is just going to be the total amount of energy transferred by heating divided by the temperature. And except in this case, so this Q up here is energy transferred to the gas by heating, which is the opposite of the energy transferred to the reservoir. So anyway, we just have to put in a minus sign to show that this is energy coming from the reservoir, all right? Energy is leaving the reservoir and entering the gas, but it's the same amount. So we get, that's why we get a minus sign. And then we're just going to divide this by T. So we get NKB ln of Vf over Vi. All right. Let me go ahead and put a small res right here. Okay. Just to remind us, this is the heat transfer to the reservoir, which is negative. And so that's just to remind us where that minus sign came from. All right, so now let's do the total entropy. All right, so this is the total change in entropy. So this is the change in entropy of the gas plus the change in entropy of the reservoir. All right, so the gas, what we had was NKB ln Vf over Vi. Okay, and then for the reservoir, we have minus NKB ln of Vf over Vi, which is equal to 0. All right, so this is an isentropic process. So this is why you don't actually see this happening in real life unless you're waiting around for a very, very long time or something, all right? Because entropy must increase for any process to just occur on its own spontaneously. Or it can remain 0, but just not likely. So, or if you take an infinitely long time, I guess, a quasi-static process. All right, so anyway, so this is why we don't really see this situation happening in real life, but we do have a situation that maybe we do see happening in real life, although it's maybe still a bit contrived, I don't know. And that is the free expansion of a gas. So what I've tried to do here is draw something about the same size as Vf. All right, so if you look at the size of these two containers, roughly the same. All right, so now I'm going to put a divider right here, and initially our gas is all on this side. All right, so this, you can think of this as some sort of membrane or something, I don't know. But basically we're going to pop it or instantaneously remove it, and the gas will be allowed to freely expand into its new volume Vf. Okay, all right, so what is the change in entropy of this process? So this is, so what we do here, because entropy is a state variable, that's why we were working out this whole problem. If we bring the gas to the same final configuration, okay, it'll have the same number of particles, of course, the same volume, the same temperature, pressure, all of these things, everything's the same, then the entropy is also the same. And so if we have two states where we start off with this VI and expand to VF, and we look at the change in entropy, as long as the two states are the same, so this initial state is this, for the gas anyway, is the same as this initial state, and the final state is the same as the final state, then the change in entropy will also be the same. All right, so for the gas anyway. So what we're going to do is break this wall and allow the gas to freely flow to the other side. One thing to note is that this is also an isothermal process. All right, you can just, so the temperature, right, is directly related to the speed of these particles. If you have a barrier, and so say, just picture a particle coming in from this side and traveling to the right. If the barrier is there or not, this is just going to continue at the same speed. So it was going to have the same speed if it bounced off the barrier elastically, right? Or if we remove this barrier, it will just continue to have the same speed, only it will just keep traveling until it hits the wall over here. So just removing the barrier without doing any work on the gas or whatever is not going to change the speed or the average speed of these particles. So it's not going to change the temperature either, right? So this is just another isothermal process. All right, so again, because we're looking at the same initial and final states, and entropy is a state variable, the change in entropy of the gas is going to be exactly what we calculated before, this one right here. And that's in fact why we were calculating it. All right, NKV ln VF over VI. All right, so there's the change in entropy of the gas. What about the change in entropy of the reservoir? Well, before, what we did is we found the amount of heat that would have to be transferred in, to create this amount of work, to push against the piston and everything. The thing of it is, in this situation, the gas is not doing any work. That's why it's called a free expansion. It expands freely. It's not pushing against anything. So with no work, the temperature is staying the same even without energy being added from the reservoir. All right, so no heat. There's no transfer of energy by heating from the reservoir. All right, so that just means RdQ on top is 0, and therefore the change in entropy is 0 for the case of the reservoir. All right, so in this case, the change in entropy for the entire universe is equal to, again, the change of entropy of the gas plus the change in entropy of the reservoir. But this time they don't cancel out. This time we just get N kV ln VF or VI. All right. So maybe there's a way we can look at this in terms of another entropy equation. All right. And that is let's go ahead and start this on a new page. So we have S equal to kV multiplied by the natural log of omega, and omega is the number of microstates available to of the system in the current configuration. So if you want to know the entropy of a configuration, as long as you know how many microstates correspond to that macrostate, you can find the entropy of that macrostate. All right, so let's see if we can use this formula. All right, so basically what happens when we instantaneously remove this divider, suddenly there's an increase in the volume available to the gas. So that lets us have more microstates. All right, so how does the number of microstates depend on the volume? Well, the number of microstates will go as the volume. So this is just for one particle. All right. So if we expand it to 2 times the volume, you have 2 times as much space for the particle to play around in, and 2 times as many microstates for that macro state. But if we have more than one particle, then for every microstate of, if we expand it, for every microstate of that particle. So just for simplification, let's just say it could be either on this side of the box or that side of the box. All right. So first, it can only be on this side of the box. So when looking at one particle, again, we double it. Now it can be on 2 sides of the box. So we double the number of microstates available to, which give the same macro state. Suppose we had 2 particles now. Then for every one of these microstates for one of them, the other one could also be in either this one or this one. So we don't just get 2, we get 4, because they could both be on this side, or they could both be on the other side, or anyway, they could flip-flop. All right, and I guess we won't really get into the whole distinguishability principle and whether they're distinguishable or not. For now, we'll just assume they're distinguishable. All right. Anyway, so it doesn't actually, for one particle, it may go as the volume, but for more than one particle, it will go as the volume to the power of however many particles you have. All right. So let's see if we can get this. So say we have a delta S, all right, and we're trying to find the entropy change from the initial to the final. So we'll look at S final minus S initial. Okay. So what we have here is we want a key B log, all right, and then I'm just going to plug V to the N in for omega, except this is the final volume, so VF to the N, all right, minus KB log. Now we're looking at the entropy of the initial state, so we have the initial volume to the N. All right, so for natural logs, we can bring down this exponent. So we have NKB, and we'll also get an NKB on this term, so I'm just going to factor it out. Log of VF minus log of VI. All right, and then again for these logarithms, this is equal to NKB. We just, I wrote log. Okay, what I mean is the natural log. You see it different ways in different books. All right. Shucks. Anyway, what I meant was natural log. So, anyway, so we get NKB natural log of VF and VI. All right, which is, so if we looked at how we calculated it this way, NKB natural log of VF over VI, we get the same answer looking at looking at it from sort of the microcanonical ensemble perspective where we're counting microstates. All right, so there we go. So this is the change in entropy for a free expansion. And yeah, so we found it two different ways. One by considering a completely different system, which we engineered, right, to take this gas from the same initial state to the same final state, and therefore have the same change in entropy. So that's one way of calculating it. We picked this weird reversible type process so that we could do our integration and get the change in entropy of the gas, right? But also we can look at it in terms of microstates, and we get the same answer for this. The change in entropy of a gas for a free expansion from an initial volume to a final volume.